Okay, all right. Well, all right, so let me get started with these examples. We're going to do a couple examples from chapter 3, a couple from method of images, and then one more kind of separation of examples, a separation of variables example. And so the example I want to look at for method of images is one where we have a spherical shell that's grounded. And with the charge outside. Right. So the idea is we have a sphere and it has a radius r. And let's put some axes on this. So we have the x, the y, and z axis. And so we have this sphere that's centered at the origin. And just like the previous example that we were talking about, we're kind of making this sphere is going to kind of have a boundary condition where it's going to be grounded. And that means that the potential at r equals capital R must be 0. Right? So if we're on the surface of this shell, then we know that the potential is going to be 0. But now we've added a charge here. Oops. We've added a plus charge on the outside, and the idea is that we would like to know the potential everywhere outside the sphere. Right? So it's important, like last time, to know where we're trying to solve for the potential, because even though the potential, we have a sphere that's grounded here, the charge is on the outside, whatever kind of image charges or whatever sort of substitute problem we come up with, the answer that we're going to get is only going to work outside of this sphere, right? We're not going to be able to get B inside the sphere, but that's okay because that's not what we're looking for. And so let's just kind of label some things here. So let's say, as we said, the radius of this sphere is R, and the distance from the origin to where this point charge is lowercase a. And so if we were to solve a problem like this, the boundary conditions are going to be important, right? So remember last time we talked about the boundary conditions. They're the things that determine this sort of unique solution. And the first boundary condition is the sphere itself that says that V equals 0 when little r is equal to capital R. And then the second boundary condition that's sort of less specific, but it always sort of holds when we're outside something like this, is that V must go to 0 as x, y, or z go off to infinity, right? Our potential has to go to 0 when we're really far away from things. And so if I just gave you this problem with this single charge and the spherical shell, a single point charge is not that difficult, but this boundary condition of having the potential be 0 on this sphere is not so easy to deal with. And so the method of images approach says that we're just going to substitute this out with a different problem that has the same boundary conditions, right? And so this is going to be the problem that we're going to substitute. So I'm going to draw my axes again here. We'll have our our x, y, and z right here. Oops. And so our point charge that we started with right here is plus q. And the idea is that we're going to add in an image charge. So we're going to put another charge in, and we're going to put it at exactly the right spot so that it creates the same boundary conditions that we had in the other problem. And so I'm going to place my image charge and I'm going to put it right here. And I'll explain exactly how large the image charge is and where it's located. So remember that our regular charge is a distance A, and then we're going to place the second charge, the image charge, at a distance B from the origin. So they're both on the x-axis, but our image charge is at a different spot along the way. And so if you remember from the infinite plane, we mirrored the charge and it was exactly the equal but opposite charge. So Q became minus Q, or minus Q became plus Q. In this case, because we're talking about a spherical shell, that's the boundary condition for the other problem, the charges are not going to be equal and the distances are not going to be the same here. And so the value of this image charge is going to be negative, meaning it's going to be the opposite of whatever, the sign is going to be opposite, but it's going to be R over A times the other charge Q. So the radius of the sphere and how far away the sphere, the charge is from the center, that's going to determine how big this image charge is compared to the one that we start with. And then the location, B, how far away this charge is from the origin, that's going to be equal to R squared divided by A, right? So again, these R's are the R from our previous, the sort of difficult problem, and the A is how far it was away from the center. So this is going to be sort of the new problem that we're going to solve. And in general, whenever you're talking about a spherical shell, this is the image charge and location for when we're talking about a spherical shell. So if I, for example, if I had another charge up on the y-axis, I would have another image charge and I might have a different distance, like an A2 or a Q2 or something like that. So I could use these formulas, these two formulas, to sort of place image charges wherever I need them so that this has the same boundary conditions. So I'm not going to derive where I got these from, but we're going to use these two to figure out what the potential is, and then we're going to show that it does satisfy the boundary conditions at the end. And so since this is just 2 point charges, in principle, finding the potential is very easy because it's just going to be 1 over 4 pi epsilon naught. And we multiply that by the first charge, the regular charge, divided by script R, how far that is away from where we're trying to get. And then we're going to add the term related to the image charge. And so we're going to have the image distance right there. And so again, I don't like script R, and so I want to kind of show where we get these things from. So remember, we talked about script R is regular R minus R prime. And remember, regular R is the field point. That's where we want to know the electric field or the potential in this case. And R prime is the source point, right? That's where the charge is located that's producing that potential. And so we have 2 charges, and so we're going to have 2 source points, but we only have 1 field point. So this is where we want to know the potential. And in this case, I want to know it everywhere. So I can really just put in variables here. So xi hat plus yj hat plus zk hat. So all I can do is I can plug in whatever value of x, y, and z I want to figure out any kind of field point I want. One kind of important thing, though, is that since we're talking about outside the sphere from our original problem, x squared plus y squared plus z squared square rooted, that has to be greater than capital R. If it's not greater than capital R, that means we're inside the sphere, and then that doesn't work anymore. Remember, we said that the solution does not work. The solution only works on the side where the original charge is from. But that's not going to really change how we solve this. Okay, so now we have a source point for each charge. So we have the R prime for the original charge, and that's just going to be a I hat, right? It's along the x-axis, so that's I hat, and it's a distance a from the origin. And then we have the r prime for the image charge, and that's also on the x-axis, so that's I hat, but it's a distance b from the origin. So we have b I hat, but remember, we know what b is. That's this formula over here, r squared over a.